Okay, good morning, everyone. I hope everyone had a nice weekend, got out and enjoyed the nice weather, at least some. Yeah, so last week we were talking about one particular method of taking a data set, which might initially be represented in some high number of dimensions, and thinking about how to best represent it in a lower number of dimensions, right? And depending upon what the structure of your data set is like, that will have relatively different properties. But in a lot of cases, this is a really effective technique for allowing you to, for example, visualize a data set, right? If a data set initially lives in 100 dimensions, people are really bad at visualizing things in more than, say, 3 dimensions, maybe 4 if you use colors. But you can actually, draw a graph if you have your data set living in 2 or 3 dimensions. There are other reasons to use lower dimensional representations of your data. For example, the space required to actually store the data set scales as a function of the dimension of your data set, and computations you do on your data set also generally scale with the dimensionality of your data set. Right? So the particular method we talked about, actually, before I begin, does anybody have any questions?
I had a quick question.
Yeah.
Yeah. So, are there so PCA is like widely used, like super widely used. Are there non-linear kind of methods that where like you project your data into some like interpretable whatever that may mean, like non-linear kind of basis, that makes it good for visualization?
So there are lots of different ways to represent your data in a lower number of dimensions. Most of the natural ones, like definitely the most common ones, are linear. However, there are other ways one might want to project data, right? So I'm not talking about it today, but there are any number of different things you can do to your data. For example, right, like I think there have been several examples where either Kevin or I have done this with our hands, right? Where we're saying that like our data lives on some like low dimensional manifold, but it's not necessarily like this, right? And there are methods for taking care of that. That's somewhat beyond the scope of this course, given that we have 20 lectures to tell you sort of the most critical bits about like the introduction to machine learning. But there are other methods that deal with some of these nonlinearities. And some of the ways you can deal with that actually involve kernels, which is a really nice use of something we saw earlier in the course.
Got you. Okay.
And just to throw out like key terms or like names of these things, popular ones like isomap, tsne, crowd kernel, or local linear embedding, or maximum volume unfolding. Those are,
gotcha,
4 or 5
there are also there are also other linear embeddings or linear dimensionality reductions that we're not talking about. We're covering PCA because it is probably the most widely used out of all of these, and it has some very natural geometric representations. But there are others, right? So randomly projecting your data does something different than projecting it onto the top k eigenvectors of your covariance matrix. Namely, it approximately preserves distances between all pairs of points, right? And that's a really nice property to have if you really care about distances as opposed to maintaining variance or minimizing reconstruction error of your data, right? And there are other settings in which that might be the more appropriate.
Like when you say random, like you literally just pick up, you just randomly generate things and just project them on that basis. Huh. Okay.
Yep. So Johnson Linden Strauss is a name. Again, if you're looking to learn more about that, right? Oh. And that's like a really elegant thing that's used in all sorts of algorithms, at least theoretically and also sometimes empirically. It's a really beautiful fact about geometry, I guess.
Gotcha.
Or collection effects, right? Technique.
And just the last thing I want to add on this point is that while we're talking about PCA today, I'm not sure if Jamie will talk about it today, but you can actually write PCA in terms of all inner products. And so now, once you can write all those computations in terms of inner products, you can compute kernel PCA, which is equivalent to projecting your data out to a higher dimensional space and then doing PCA there. And that can pick up these nonlinear manifolds that Jamie and I are very unvigorously alluding to.
And miming in some, or acting, I guess we're using our words as well, but
gotcha.
Okay. Yeah, interpretive dancing. Okay, so good. Any other questions? Okay. Right, so let's, with that, go back to some of the more technical underpinnings of PCA, because we just sort of briefly touched on it last time. Okay, so recall that PCA, if we're thinking about PCA, it sort of has two equivalent views, both of which are useful in different contexts. One of which is that you're looking to project your data down onto a k-dimensional subspace, such that you've maximized the remaining variance in that projection of your data points, right? That's equivalent to finding that d-dimensional subspace for which your average squared distance from your original points to their projection is as small as possible, right? So this first one's called sort of maximizing the variance of your projection, and the other one refers to minimizing the reconstruction error, or minimizing the distance between your points and their projections, right? And these are equivalent, and in different contexts will be useful. Okay, so if we want to write this out more mathematically, right, what we can say is that we are looking at our normalized data points, or sorry, we've subtracted the mean from each of the data points, right? And then we're looking to project those data points into some q-dimensional space, okay? And that can just be written as the following optimization problem, right? And these two, via some simple linear algebra, are equivalent. And if you do some analysis on this second term, you'll notice the way to minimize this quantity, this trace of sigma minus trace VQ transpose sigma VQ, is to use the top Q eigenvectors of your covariance matrix as VQ. And that will allow you to capture the most variance in your data with Q vectors that are all orthonormal, right? Right. So the reason we need this orthonormality constraint is that, like, you know, if we've captured the most variance in one direction, we want to make sure that whatever optimization we're doing doesn't sort of capture that again and again, right? Because you're not getting additional information by sort of always moving in that same direction. You want to, you know, sort of ignore that direction and only think of directions which are really orthogonal to that direction. Okay. So given our data, right, the solution, or the minimizer of the reconstruction error that we might want, looks to find the first Q eigenvectors of our covariance matrix. These are also called the first Q principal components of our covariance matrix, okay? And PCA is something simple, right? PCA just projects our data, once we've removed the mean from each of the data points, down onto this Q-dimensional subspace. Okay, so, you know, this is kind of the lazy person's version of how to draw a slide, but so PCA basically just says, okay, so we have a data set. We're going to look at the covariance matrix and find the largest eigenvalues, right? And those are going to be the dimensions in which we'll represent our data set, or sorry, the directions in which we'll represent our data set, right? And if you want to be computationally a little bit more efficient, you can decide whether you want to do that computation on X transpose X or on XX transpose, depending upon whether A is wide or long, right? So if M is greater than D, right, then that's just going to mean that X transpose X is a D by D matrix, right? And if not, then XX transpose is an M by M matrix, right? And computing, you know, in the case that D is smaller, this is a better computation to do in general, right? Computing on a lower dimensional matrix. If M is smaller, then you'll want to do something on an M by M matrix, right? And in both cases, this is just saying, find the eigenvectors of this matrix. Okay, so I still haven't told you actually how you compute eigenvectors, right? So that's going to be what we'll spend a bulk of the next 40 minutes or so doing. So there are two pretty natural ways to do this. We're actually going to start, you know, I ordered these basically according to the one that is sort of more computationally manageable for a really large data set is actually power iteration. And we'll talk about that in a minute. But I'm going to start by telling you about a fundamental fact about matrices, which can be used to compute your top k eigenvectors, or in fact, all of your eigenvectors simultaneously, because it is so fundamental to not just PCA, but sort of a more general understanding of matrices that's sort of used. I can think of very few places where the SVD is not relevant in machine learning. Okay, so if you have a matrix, right? So this is just a fact, independent of PCA entirely, right? So if you have some matrix, right, that is in M by N dimensional space, right, with rank R, right? So R is going to be at most M and N, right, the minimum of those. You can write A in a really nice way, okay? So we have some matrix A, right? And we can write A as this somewhat strange looking product, right? Where we have a matrix U and S and this V transpose, okay? So this is just the, I haven't parsed the rest of this statement for you, but this is the picture I want you to have in mind, right? So A is some matrix. We have U, S, which is long and thin, and VT, which is smaller, right? Okay, so the matrices are going to have some very specific properties. Okay, so S, apologies, sorry, I just made, okay, right. So U is going to have the property that all of its columns are orthonormal, right? That's what this means. Okay. And V is going to have the property that both its columns and its rows are orthonormal. But this is, you know, that's a fact that is even stronger than this statement here. Okay. And can somebody remind me what orthonormality means? Go ahead and answer. Anybody? I know somebody knows this.
It means that the if you take the dot product of two different columns, it will be 0. But if you take the dot product of the column with itself, it'll be 1.
Exactly, right? So these sort of operate as like a basis in the canonical sense that you think of a basis. Right? Okay, so that's what these two things mean. then S is going to have a really particular structure, which is that it's going to be diagonal with positive entries only on this diagonal here, okay? And this is a really nice property to hold for a particular matrix A, right? Because, so if we, this is M and this is N, right? This is N, this is M and M. I'm just writing out the dimensionality of these things, okay? And then N, this is n-dimensional right here and n-dimensional right here, but this is n minus D, sorry, n minus M.
So actually,
sorry, I screwed something up. Yeah.
No. So there's
two ways to write this down.
Yeah. James writing down the so-called like full SVD decomposition dimensions.
Yeah.
But you might be confused if you're looking at the theorem statement because it says that S is a R
by R. Yeah.
Because this is the so-called skinny representation of SVD. And this is just saying like in. Yeah, I mean, Jamie can.
There we go. Yeah, sorry about that. Yes. Okay. So basically, because A is only R dimension, sorry, A only has rank R. What we're going to look at here is actually just like the thing that corresponds to those R dimensions. Okay. So in that case, what we want is that we're just going to write R and M by R dimensional thing here, and then good. Okay. Apologies for that. Okay. So this is a really nice decomposition, and it has many uses. But one of them is that it has a natural relationship with eigenvectors. Okay. So we're going to look at that, okay? So let's start by looking at what A transpose A is, okay? So A transpose A, right, just by this definition, is equal to USV transpose, V S transpose U transpose, U S V transpose, right? All I did was write down something simple here. Okay, so we know that U transpose U is equal to the identity matrix, right? That's true right here. S transpose S, I want to define to be equal to D, right, for the remainder of lecture, right? That's like going to be a useful thing. And remember that S is this diagonal matrix. So S transpose S is just another diagonal matrix with like the squared same values on the diagonal. Okay, so then we have that A transpose A is just equal to V D V transpose. And if we do the same computation for A transpose, right, then we get U S V transpose times V S transpose U transpose, right? We know that V transpose V is again equal to the identity. SS transpose, right, just as before, is also equal to this matrix D. S transpose is equal to S transpose S. And this is equal to U D U transpose. Okay. So why am I doing all of this? Well, in general, it's pretty nice, so far when we've looked at like most of the algorithms and most of the representations of things we've looked at in class, we've looked at X transpose X or XX transpose. Those show up everywhere, right? So if you have your matrix X in its SVD format, right, or if you've sort of already done that computation for X, you can very naturally write down X transpose X and XX transpose as these nice compact representations as a function of these pieces of the SVD. Okay, and that's a nice fact, right? But I still haven't really told you much structurally about the SVD yet, right? So if you look at, so we've already computed A transpose A, right? If we were to compute A transpose A, let's see, I'm going to move some things around a bit. Okay. If I were to compute A transpose A V, right? That's just equal to VD V transpose V, right? And V transpose V again is equal to this identity, right? Because V has rows and columns which are orthonormal. So this is equal to VD, okay? Which means, right, A transpose A VI, if we were to add an I here, just gives us this, right? So we get VI DI I, which is equal to VI SI I squared. Okay, so what does that mean? Can somebody tell me, can somebody remind me what this equality means about the vector VI relative to A transpose A? What is their relationship? Oh, sorry, go ahead.
It's the eigenvector of A transpose A.
Yeah, right. So VI, which is this ith row of our matrix V, is an eigenvector of our particular matrix A transpose A, okay? With eigenvalue DII. So that's cool. What about this other one, right? So we did the same computation, or a very related computation right here. Okay, and if we wanted to compute A transpose times U, right? That's just equal to U D U transpose U. Again, this is the identity because all of the columns are orthonormal for U. So this is just equal to UD, right? So again, if we're just looking at the ith component as opposed to the entire matrix, that gives us that this is equal to UI SI I squared, right? Which also means, right, that the U's are the eigenvectors for A transpose. Okay. So let's sit back and think about this for a second. So for any matrix A, we can represent it as the product of three matrices. Two of them have orthonormal columns, and those orthonormal, those represent, those matrices actually contain all the information you need, right? They have all of the eigenvectors for both A transpose A and AA transpose, right? And the eigenvalues correspond to the squares of the diagonals in that third matrix. Do people have questions about this? I understand that this is like, if you haven't seen the SVD before, it's definitely not totally obvious that this would be true.
What is the difference between projecting on the left, like the U versus V? Like, because you know, in the thing you talked about like skinny versus wide, right? Like, what's the difference between those two?
Yeah, so basically, you don't, so that's a good question. So skinny versus wide has to do with like whether you do this entire, so you know that like, X is an n by m, right? And if X is an n by n dimensional matrix, right, we definitely don't have to compute more than the min of m and n to get this projection, because for a variety of different reasons, right? Yeah, so computation is one of the reasons, but that's somewhat different than the other question you asked, which was about left versus right? So U is normally referred to as the set of left singular vectors, and V the right singular vectors of the matrix.
Thank you.
Yeah. Right. So there are two, we've sort of, Kevin alluded and I like made some mathematical mistakes because I was reminding myself I switched between M and N. I switched between M, N, and D when initially writing this down in my notes. But there are, you can either compute the full SVD or you can recognize that sort of if you have matrices that are much longer than they are wide, you can actually do a cheaper computation and sort of you know something about right, if we go back and look at this picture, right? I ignored, right? So there are two theorem statements, right? This is about what's so-called the skinny SVD, right? Which sort of only takes into account, because the matrix has rank R, you can sort of represent it more compactly than if it had rank equal to the min of M and N, right? And so that's why we sort of have this like nice compact center matrix, right? That everything is a function of R rather than just M and N, right? The dimensionalities of these things. Okay. So, right, we've convinced ourselves via some basic linear algebra that V contains the eigenvectors of A transpose A, and U contains the eigenvectors of AA transpose. Okay, so what does that mean? It means that once we've computed the SVD of X, right, our original data matrix X, then we can do some really basic calculations, right? Via some basic matrix. We already know what the top R eigenvectors of our covariance matrix are, right? Okay. So what that means, right, is if we want to use the SVD to do PCA, well, once we've done the SVD, we already have the top R eigenvectors of X transpose X, right? And of the covariance matrix. I'm flipping back and forth. I apologize. There's a question of whether or not you've subtracted the means from all of your data points initially, right? Right. So if you have the covariance matrix, right, and you look at finding the top K eigenvectors of that, the SVD provides it for us already, right? It's the first K rows of U. So what is the computational complexity of using the SVD to actually do the computation of finding the top K eigenvectors? So the SVD, right, does some computation, right? This economy size SVD that we were talking about takes time that depends on N, M, and R multiplied together, right? And remember, A was originally N by M, so N times M is like the amount of time you need to even read in A, right? And then we pick up an R where R is the rank of our matrix. So note, this is independent of K, right? Because if we use SVD, right? SVD is just like a use once computation for a matrix, and it gives us all of the eigenvectors of that covariance matrix, of the covariance matrix of the matrix. Okay, so you can, in any number of different languages that have basic linear algebra, you can ask for the SVD, and you sort of get this SVD once, right? But this might be much higher than you want, right? If your matrix actually is high dimensional, R might be pretty big, right? And you might not want to do this computation in this way for exactly that reason, right? And in fact, right, I've alluded to this idea that like maybe you want to use PCA because your data was initially represented in such high dimensions, you just don't want to do computations that depend too heavily on R, right? So is there a way to do a computation of the top k eigenvectors of our covariance matrix where we don't sort of pay for the total rank of our initial covariance matrix? Right? So that's the question, right? Can we sort of also, you know, if we're using PCA, right, we probably don't want to decompose our entire data matrix in terms of all of its eigenvectors, right? We only care about the top sum number. Okay. I'll tell you about that in a moment. It's also somewhat instructive, right? And your current homework asks you to do some things related to this particular slide, so it might be useful to glance at it. If you run PCA on a data set such as MNIST, right? If you think about like the set of images of the digit 3, right? You can actually, you know, you can do PCA on that data set, and what you'll find is that the average value of the 3's in the data set looks like this, right? And if you want to capture the most variance from the remaining subtracted off values for all of the 3's in the data set, you'll end up finding that these two images are sort of the most relevant images for capturing the most variance between the 3's in your data set, right? So you can actually represent all the 3's in the data set as some linear combination of these two right-hand digits plus this mean, right? And it won't be a perfect representation, but it does a reasonably good job, right? Okay. So, you know, this is just what the 3's look like when they're projected into two-dimensional space, right? This right here. Okay. Okay, does anybody have any questions about that before I move on to talking about another way to compute the principal components of a matrix? Okay. All right, so as we were saying, oh, actually one more thing before I talk about that additional, way to do this computation, right? Just remember that the singular value decomposition that we're going to be thinking about is we take our matrix X, we subtract off the mean, and then we look at the SVD of that remaining matrix. Okay, and here's a nice image that sort of represents what's happening here, right? Namely that U1 and U2 just correspond, you know, we can project this data onto, you know, from 3D onto 2 dimensions, and this is what that process actually looks like, and the resulting data once it's projected down. Okay. So now I want to talk about, in some ways, a more practical way to compute the top k eigenvectors of a matrix, right? If SVD is too computationally intensive, or you think that you might only want, say, 3 eigenvectors because you're going to use them for visualization or something, and you know your matrix has high rank, how should you do this, right? If you don't want to pay in a way that depends on the rank of your matrix. So the answer is something called the power method, which computes these vectors one at a time, as opposed to computing them all at once, which is what the SVD does, okay? So we're only going to look at one vector, and we're going to say what we want is to find the single vector which maximizes this quantity, right? So this is capturing the most variance from our covariance matrix possible. Okay. So the power method is just an iterative way to find the vector that maximizes this quantity, right? So it starts with some nice vector that's drawn from, say, you know, there are various ways to initialize this, but suppose we take a vector that's drawn from a nice Gaussian, and then we're going to define a sequence of vectors which are going to get closer and closer to maximizing this quantity, right? So we'll say that Z1 is equal to, just according to this box right here, Z1 is going to be equal to the covariance matrix times Z naught over the norm of the covariance matrix times Z naught, right? And then Z2 is going to be equal to the same thing, right? But replace Z1. Okay, so this is like a sort of strange thing, right? It's taking some, you know, it's certainly not going to be, it's not obvious entirely what this is doing, right? But, you know, if we want to sort of follow our nose, right, this is, there's a nice way we can interpret this, right? And this is the way we want to do this is as follows. Okay. So remember that, right, this is X transpose X, right? Our covariance matrix here. And we showed before that when we represent our X as USV transpose, right, that the covariance matrix can be written as VD V transpose. And this is again S squared, right? Okay. So this is just a statement, right? This is for analysis purpose. We don't actually want to compute the SVD of our original matrix S, right? But this is just a way to analyze what the power method is doing, okay? So we can think about our covariance matrix this way. And we can also represent ZT as a linear combination of the vectors in V. Of the, right? And that's simply true because V is an orthonormal representation, right? It has orthonormal columns. So this is just, so we can actually just say that, like, we're going to look at this representation of each of our vectors, right, as we iterate. Okay. So if we write dt plus 1, right, that's equal to, it's equal to V alpha t plus 1, right? And it's also equal to the covariance matrix times ZT over the covariance matrix times ZT norm, right? Okay, so what do these things mean? We can also write alpha t as equal to V transpose ZT, right? Just multiplying by V transpose on both sides of this, right? And if we look at alpha t plus 1, right? That's equal to V transpose ZT plus 1, right? And we can write ZT plus 1 as V, sorry. Okay. So we can write this as VT times sigma ZT over the norm of sigma ZT, right? I'm just using this iterative definition here, right? So that is equal to, right? So if we look at V transpose times sigma gives us the diagonal times VT, right? And ZT is equal to, sorry, maybe this is easier to write this over here. Okay, so if I write V transpose sigma, right, that's just equal to V transpose V D V transpose. These again are equal to the identity, right? So we then have dv transpose, right? And if we multiply that by zt, right, v transpose sigma zt is equal to dv transpose times v alpha t. And again, this is the identity. So the numerator of this whole thing is equal to d alpha t. Right? And I'm not going to show you why, although it's a pretty basic calculation that has to do with the fact that the norm of the product of two things, one of which is orthonormal, will drop out the orthonormal term. The denominator of this is also equal to the norm of d alpha t. Okay. So, you know, what did I do here, right? I said that each of the iterates zt could be written as a linear combination of the columns of v, right? And then I said, okay, so what are the linear coefficients of those different iterates, right? And I wrote alpha t plus 1, these coefficients, as a function of this diagonal matrix squared and the previous coefficients, right? If I actually roll that back and say I want to define this not just in terms of alpha t, but alpha naught, we can also show, right, just by doing some basic induction, that this is equal to d to the t alpha naught over the norm of d to the t alpha naught. Okay, so you can basically roll back what your coefficients are going to look like in the t plus first iteration, just in terms of this nice diagonal matrix, which has this, you know, which is just s squared, and your initial coefficients. Okay. So why does this work, right? Why is this procedure actually doing something meaningful? Right? So this is just a nicer representation of the thing I just wrote, right? That alpha t plus 1 is equal to this guy right here. But what does this look like? So dt, right? You can just rewrite that as multiplying by d11t and then dividing by d11t. And then you can show, and there's sort of a natural way to show this as a function of the number of iterations t you do, that this converges to d11 raised to the power t, e1, where this is the standard basis vector, e1 transpose, right? And the reason that happens is that, you know, remember that S was the set, S contained the eigenvalues for my matrix. And I don't actually know that I mentioned this, right? But they're actually in order, right? So, you know, I guess you could rewrite a lot of this regardless of the order, but let's assume that the eigenvalues are sort of ordered greatest to least, right? If that's true, then d11 is going to be the largest value of any of the squared eigenvalues on this diagonal. So this is where this particular, where dii divided by d11 being less than 1 comes from, right? That just means that sort of this term is not going to, you know, the only meaningful direction is going to be in the first direction. Okay, so what this is suggesting is that like alpha t plus 1, right, is going to be starting to look more and more like our first eigenvalue split. So that's good if we're actually looking for our eigenvector. Okay, so this is another way to compute, you know, sort of the top eigenvector of our matrix. The way you would actually turn this into an algorithm to find the top k is that you would do this for some number of rounds. You decide that your top, you know, the vector you've computed has normalized, or sorry, has sort of stabilized enough. You're not sort of seeing lots of changes between the different iterations, right? You then want to sort of subtract off that quantity from your matrix and start again, right? If you want to find more than just one eigenvector, but you want to find multiple eigenvectors. Do people have questions about this? Right, the power method is, if you're a computer scientist and you're used to like iterative procedures, this is maybe fairly natural. If you're not a computer scientist, you might be trying to understand why we wrote this recurrence relationship, but the answer is that like it's pretty easy to like implement this as like a basic program. Questions?
Teacher, I have a question.
Mm-hmm.
So in the power method, like finally the ZT, when t goes to infinity, ZT will how to say converges to the direction that has the maximum variance. And how about the singular values corresponding to that vector?
Yeah, so the alphas, like alpha t, will also like move in that direction.
Oh.
Right, that's what that, yeah, I think,
The alpha t is the singular value?
No, let's see. No, so the singular value, right, so you'll get out the singular vector or an approximate singular vector. From that, you can definitely compute an approximate singular value, although I don't know if we have it directly here.
Just by the definition, like A transpose A times the singular vector, and all right. Thanks.
Other questions? I know that both the SVD and sort of various, things about the power method are somewhat opaque if you haven't seen them the first time.
I had a quick question.
Mm-hmm.
Just about that alpha, could you quickly explain its role in the equation again?
Yeah, so we're just saying that we can write ZT in a way, sort of in the basis represented by V. Right? So we're just saying, okay, we want to represent the vector we're thinking about in round T as a linear combination of the space, of the various vectors in V, and alpha T just corresponds to sort of how much we're weighting those different directions. Does that help?
Yeah, I think so. Thanks.
Mm-hmm. And that might not have been the clearest answer. If Kevin, you have a clearer answer, that's fine too. Go ahead and jump in.
Sorry, I was focusing on the chat, so I just didn't hear it.
Okay. Okay. I think the question was about the role of alpha T in this, and I was just saying it corresponds to sort of how, we're writing ZT sort of as a function of the basis represented by V, and alpha is telling us sort of how much we weight the different directions.
Yep. Very much like kernel methods, where alpha is playing that role of just putting weights on the relative basis. And there was a question that maybe I'll just point out in the chat about, why is this more computationally efficient than just computing the SVD? I guess it's not obvious because like how many iterations do you need to run for and this sort of things.
And there are lots of matrix multiplications, maybe. Yeah. Right. So that's a great question. So we're not going to show the analysis, although I think actually last year's lectures have a nice analysis of this, or at least maybe state the fact. Maybe they just state the fact that you need like so the number of iterations you have will directly correspond to sort of how close your approximate eigenvector is to actually being the eigenvector, or have it capturing all the variants you care about. But in general, the number of iterations you need doesn't depend on R, the rank of our matrix. It depends on N and M. right? And you generally only need like roughly logarithmically many iterations before you get quite close, right? So what that means is you need like some function logarithmically of n and m of these iterations for each of the vectors you're going to compute. And then, you know, you have to do some calculation here about how much computation each iteration takes. Well, again, you know, we are doing, you know, let's look, right? So this is the algorithm, right? The rest of this stuff is just analysis. We're not actually doing the SVD. Here, we're just taking the covariance matrix, we're multiplying it by ZT, and then we're taking the norm of that matrix too, right? So that's going to be some computation, which presumably takes time, n times m. You know, it's going to be some function of n and m, but doesn't necessarily need to depend on r. So the whole point of all of this was like, we want the k eigenvectors that correspond to the top k eigenvalues. And we'd ideally like to do that in a way that sort of doesn't depend on the entire dimensionality of our original matrix. One way to do that is to compute these one at a time rather than to get all r at once. And you know, this, you know, each iteration is going to have, each time we want to compute one of these eigenvectors, we'll do like logarithmically many iterations of the power method, and each iteration takes some time that depends on n and m, but not r. Right? So then the total time, if we wanted to compute the top k eigenvectors, is going to be like k times some function of m and n, depending upon how you do these matrix multiplications, times some logarithmic factor. Therefore, like circumventing the need to depend on the dimensionality of our original matrix. Right? And I agree, it's like not obvious, right? This seems like a more complicated thing, right? The SVD is like, oh, this thing exists. There's like a simple package or a simple like command in any natural language you'd be using to process matrices for the SVD. It's really simple. But the power method doesn't make you sort of compute the full SVD of your matrix. You can sort of say, I want the top singular value, the top singular vector, or the top principal component. I want to understand sort of how much variance in my data set that captures. And you can decide, is that enough? Is that not enough? Do I need another singular vector, right? And you can do a lot less computation that way if you sort of suspect you're going to need many fewer than r of the top singular vectors.
Yeah, and this is known, I think a rite of passage for every machine learning person is to naively just import your data, your like 100,000 by 1,000 dimensional data matrix, and try to compute its SVD, and then watch your computer melt. The SVD is just basically one of the hardest things a computer can do that's still computationally tractable. It's harder than an inverse of a matrix. It's like all the things that we think of as being like the hardest things possible in linear algebra, like SVD takes the cake. Because once you have the SVD, you can very quickly convince yourself, if you have the SVD, you can quickly compute the inverse of a matrix trivially. You can solve AX equals B trivially. Once you have the SVD, you can do all these magical things. That's why it's so fundamental. But like it's a hammer. It's very much like it's a beautiful sort of decomposition, but it's computationally very, very difficult for a computer to run. And so you just have to be smart about like what you're asking for. Before you hit enter on computing the SVD, think a little bit, because your computer may not come back.
I don't think you'll actually kill your computer. Like, I don't think you'll do permanent irreparable damage, but it may be the case that your computer hangs.
Yeah, you may have to like press and hold the power button for a while to get out of it.
Right. So save your work first.
Yeah. So like,
right.
And so what Jamie's talking about, there's a lot of things to think about. She was talking about the different sort of dimensions of thing. You can look at the inner product matrix, which would be XX transpose, taking the SVD of that. That's an n by n matrix, or looking at the covariance matrix, which is a n by n matrix, if it's an n by n matrix. Or the one of those could be much smaller. M squared could be smaller than n squared, and which would be smaller, and then that's also smaller than m times n. So like thinking about these things is actually really important before you just do it naively. And then also besides that, then you also have this thinking of like, well, I only really need the first 4 eigenvectors because I'm going to be doing PCA and I'm going to be plotting it in 2 or 3 dimensions. So I don't need the top 1,000 eigenvectors. And so the package that can do this in NumPy or SciPy is SVDS. And that's where you give it the matrix and the number of eigenvectors that you want to compute. I think in this class, we'll probably not give you any homework where like we're going to break your computer or run out of memory. But
if you do it, well, I mean, I also agree that's probably true. We probably won't break your computer. But right there, I wonder if that's true if you do homework in arbitrary ways, right? Like it's possible that like if you didn't think about like which dimension was much larger, I'd have to think about it. I don't think we have a problem where like in either dimension it would be a problem.
Yeah.
Now I'm thinking about it.
Yeah, I mean, taking the eigenvalue decomposition of a 50,000 by 50,000 matrix, you will definitely run out of memory. But
yeah,
you won't even be able to allocate that matrix, most likely.
Yeah.
So like it would break before you even get to the SVD step.
Yeah.
Anyways, these issues that we're talking about though are like very much on the minds of people that are working in optimization on like large scale machine learning, because like the power method is one of the algorithms used at the core of all of search. So Google uses the PageRank algorithm because of Larry Page of Google, and basically it came from a machine learning paper. It's an algorithm to compute. Basically, the first eigenvector is the scores attached to each website, and like if it's relevant, you compute the graph, the adjacency matrix, and then you do power iterations on it. You're basically just taking SVD, and that top eigenvector corresponds to the most relevant sort of ranking sort of thing. And it's doing this all the time. And there's one other question about like, oh, what if M is really big, like all the pages on the internet? Well, stochastic versions of these, so you're never actually computing entire matrix, you're just taking batches of the matrix at a time.
Right, and there are other ways to compute approximations of like eigenvectors of a matrix, right? The power method is one, but as Kevin's alluding to, there are many others which, like, depending upon precisely what you want and sort of the relevance of the various dimensions, right? Like how big various things are and what kind of approximation you need and all sorts of other things, there will be different trade-offs you could make. Okay.
For the homework,
yeah.
Are we like implementing the power method? Is that, or like whatever, like are we implementing SVD for the homework? For the PCA thing, what are we doing? Or can we use a package is my question. Or are
you
we
can use
this?
SVD.
You can use SVD.
Cool. Okay.
Do not, I mean, like, there's been some questions that always kind of make me smile when I see them on Piazza, where it's like, for instance, like, can I use a package on PCA? Like, well, PCA is just SVD.
Right.
So like, it would be more lines of code because you do now import a package to run PCA. Like, just run SVD. Because it's a native sort of like a fundamental thing, as Jamie is getting to. It's involved in everything. So just run SVD. And same thing as like something like kernel ridge regression. Like that's a one-liner. That's solving A equals B. There's no need to run a package for these things. And this is as great as scikit-learn has been for the community. This is like one thing I don't love about it is that like it's very easy to get used to just calling out a package and forgetting that like it would be faster just to like solve A equals B than to run these things. But
right. But it does depend, right? So like one of the points of what we've just been talking about is that like SVD can be computationally super expensive, right? So like there are definitely times where you won't want to run like SVD, but like it's not obvious that like what you want to do either is necessarily just like call up to some package, because that package might just like compute an SVD on the back end, right? It's important to understand how those things are actually doing these computations. You know, SVDS isn't actually going to compute all of the R eigenvectors. It's going to just compute the top S, right? So that's doing something fancier, and it's important to remember that, like, you know, a package is only as good as its implementation. Okay, good. So I have one other thing that I want to tell you a little bit about, and I'm just sort of going to allude to it because you have a problem about this on your homework, but I think it's natural to understand sort of its relationship to PCA. So this, you know, Netflix is a particularly relevant application in our lives right now. So you probably were all just about, well, I don't know. I won't try to guess the median age of the people in this classroom. But long ago, there was a challenge provided by Netflix, which was the following. They had this huge partially completed matrix, which corresponded to all of their users, right? And all of the movies they had watched. I think at that point, Netflix was really just movies. And the corresponding ratings that the people had given the various things they had watched, right? And the, you know, in general, right, only about 1.2% of all the videos on Netflix were watched by any particular person. Again, these numbers are based on like when Netflix was a smaller volume of movies, and people hadn't been sitting in their homes for 2 months and, you know, finishing Netflix. So the question was, how easy is it to predict what movies people will like based on what they have watched and rated so far? Right? So, you know, there's this really large dimensional matrix which maybe corresponds to all of the possible ratings, or, you know, all of the ratings you would give to every person who watches things on Netflix would give to every movie on Netflix if they watched them. And Netflix wanted to know how to predict those from the set of ratings they currently had, right? And they were going to use this to, for example, make recommendations that were like more tailored to you than saying Tiger King is the #1 ranked thing on Netflix. I guess that was maybe like 2 or 3 weeks ago. There's a lot of churn on the top end for Netflix right now. Anyway, okay, so how do we do this, right? Like, what is this problem actually saying, right? It's saying there's some high dimensional, you know, there's some, there's number of users, and there's a bunch of movies, and, you know, some of these entries are full, and some of these entries are question marks, right? And the question is, how do we fill in the question marks based on the information we have so far? And the short answer is, if we make absolutely no assumptions about anything, you know, if we make no assumptions about the users and we make no assumptions about the movies, in theory, it could be possible that like everyone's preferences for every movie are totally uncorrelated with one another. Right? In which case, we could say absolutely nothing about the empty or the question marks in our matrix. However, right, human beings are not sort of arbitrarily complicated usually when we're talking about their preferences for movies, right? It's quite likely that there's a much lower dimensional representation of our preferences than like sort of a different number for every movie on Netflix that could be arbitrary. Right? Instead, it might be the case that sort of we have a set of preferences over maybe genres of movies, for example, right? Maybe I really like horror movies and I really hate romance, and I like comedies somewhat, right? And every movie can be represented as some linear combination of which of these genres it falls into, right? If that's the case, right, then this really large dimensional matrix that we initially started out with, S, right, should have a nice representation. You know, we should be able to represent the preferences of every individual for every movie as like a much lower dimensional thing than all of S. So given n movies and n users, right? The Netflix challenge was asking how to find the following two matrices, right? U, which is an M by D matrix, and V, this is V transpose, where this corresponds to users, this corresponds to movies, right? So basically a way to represent the users and the movies on Netflix in, you know, sort of something that represents something that's related to D, such that something that looks startlingly familiar maybe to us, right? This looks a lot like reconstruction error. Right? The question was, is there a way to represent all the users and movies on Netflix such that this dot product sort of minimizes the reconstruction error over what's already known? Okay, so how would we do such a thing, right? How would we find U and B which minimize this reconstruction error? So if we had all of S, right? If S didn't sort of have question marks, right? So if we had full information, like S is in R and M, right? So i.e. we have all the ratings. What we'd want to do to minimize reconstruction error over S, we understand that already, right? If we're looking for a D, like a much lower rank representation of S, we should run PCA, right? We should find the top D eigenvectors of our matrix X and use those to represent both users' preferences and movies in that space, right? Users' preferences over those vectors, and then movies as a function of those vectors as well, right? If we don't have all of S, right, we need more information, right? You know, one of the things I mentioned was like, you know, if things are totally uncorrelated, right, we could be in trouble trying to, you know, reconstruct something that actually does a good job predicting other people's preferences or predicting preferences that we don't know yet. But there are other ways we could be in trouble, right? Like if we have if S is far too sparse, right? Like we have many missing entries, right? It's possible that this will not be a well-defined problem. On the other hand, if we assume S has relatively low rank, right? Right, so PCA. If not, we need some assumptions. Right? We need that S, maybe like the rank of S is something like K, right? And we certainly need to have enough entries in S that we can sort of say something meaningful in K, right? So sort of the number of entries in S needs to depend on K, some function of K, right? Or this problem won't even be well defined. So, you know, I think I'm not going to say more about this precisely. I know that there's a question on the homework about this, but, you know, there's a question of sort of how, you know, which entries were removed from S, meaning like, you know, if we imagine the process of like people watching things as like uncovering, we could also think about like randomly covering pieces of our matrix. Depending upon how that behaves, we can argue about, or we can talk about ways to come up with this representation UV transpose, which approximately minimizes reconstruction error. Does anybody have any questions about this? Okay. So a couple of takeaways before I briefly mention sort of another paradigm in ML that's sort of useful as like sort of cultural knowledge, if nothing else. Okay, so PCA finds a d-dimensional representation of a data set, which simultaneously has the highest variance of any d-dimensional representation of that data set and the lowest reconstruction error in a d-dimensional representation of our data set. It's spanned by the top d eigenvectors of the covariance matrix. Right? And the way to compute these eigenvectors is to do one of two things, right? At least as far as we talked about in class. One is to compute an SVD, and the other is to use a power method, the power method. And, you know, yes, the power method is like, you know, more complicated to understand than writing SVD, but there are lots of reasons you might want to use the power method in practice, even if you can get away with using SVD on the homework. Okay, this is one way to represent data in lower dimensions. There are many others, right? As I mentioned briefly, I think in response to Baraj's question, right? If you don't care about sort of capturing the most variance or minimizing reconstruction error, but care about some other property of your projected data, you can instead think of other ways to project your data, linearly or non-linearly. All right, so now I'm going to tell you briefly.
Amy,
oh, sorry,
before
Kevin.
moving on,
Yep.
I just want to say one last thing on that. Could you go back a couple slides? Yeah, that's great.
Great.
So you might, because, you know, Jamie so clearly made the connection to reconstruction error, like this is something that we've seen very frequently before with least squares. And what we did there, if we wanted to minimize this expression where we had like, you know, xw minus y with respect to w, we just take the derivative and, you know, maybe set it equal to 0 if it was least squares, or if it was logistic regression, then we would take gradient descent and we would go to the bottom. SVD is a very interesting function in that this is actually, this objective function with respect to u and v is non-convex, okay? So if you just took the gradient of this thing and did gradient descent, it's not obvious that you'd actually get to the bottom. But SVD is basically anytime you see like that you're, anytime a paper is claiming that they're doing non-convex optimization and reaching a global minima, 9 times out of 10, somewhere hiding in there is they have reduced the problem to SVD, because it is basically one of the only non-convex problems that we know how to solve, and you actually get a global maxima too. And that's why it's sort of amazing. And so even though this is like SVD, this problem with major completion is basically SVD. It's the least squares problem. If you run gradient descent on this, it's not guaranteed to converge to the bottom because it's non-convex. It can get stuck at a saddle point, but 9 times out of 10, it will maybe do something reasonable. It does get stuck in local minima. If you run
but those local minima always have really nice properties, right?
Yeah.
So like one of the like most beautiful facts that like it took me a long time I still don't think I totally have internalized it, is like that the local minima of this thing still like live in the span of like the top d eigenvectors. There's some like really nice properties like this.
Yeah, so just as Jamie was saying, you know, you run SVD, you do power iteration, you can do gradient descent, and that is a lot of times what we do in practice. But you should just be aware that like you might end up at a local minima, unlike if you run power iteration or SVD, where you're guaranteed to actually end up at a global optima. But it may just just different algorithms.
Right, different properties, right, and sort of the local optima when we're talking about reconstruction error are generally much nicer than for other non-convex problems, right? Nicer meaning that they have like better guarantees than we normally know how to get for other non-convex optimization problems. Also, Kevin reminded me briefly, so I drew a picture because I thought he was going to talk about something else, that PCA is minimizing this like error where we project points like sort of in the closest possible way to some dimension. Least squares just does this, but only in the dimension of y, right? So we're trying to do some prediction of some value y from x, and least squares is trying to do some prediction, and like the projection isn't sort of the closest distance to the point, it's the y distance, right? From the prediction to the actual value. Sorry, I thought you were going to talk about that when you talked about least squares. Anyway. So this is sort of a nice picture to have in your mind, not that it's like relevant to anything else on this slide. Okay. All right. So I'm going to, now very briefly just introduce a way of thinking about a collection of problems that's related to one we've already talked about. So remember last lecture, we were talking about Lloyd's algorithm for minimizing, or at least approximately minimizing the k-means objective, right? And the way that worked was first randomly pick some centers, assign points to those centers based on which ones are close, which center is closest, then recompute a center to be the centroid of the points belonging to that center, and iterate. Right? So this is just this is an algorithm which sort of belongs to this template of algorithms, which are sort of much more pervasive in machine learning, which are called expectation maximization algorithms, right? And what that means is like, what Lloyd's algorithm does, it fixes centers and assigns points to, I'm putting this in quotes because this is a very like wishy-washy statement, the most probable cluster if we fix the centers. And then fixing those assignments compute the most likely center, right? So both of these statements have to do with some like likelihood function, which I haven't defined, right? But like, bear with me. I'm just trying to give you some intuition as opposed to like being super formal about this. Okay, so this is just a form, this is sort of a more, belongs to a class of more general things where we first do something which is called expectation, and the second is called maximization. And we basically go back and forth between expectation and maximization, right? So if there in general is a data set you have, and you believe there's some data generating process which produced it, but some of your data is missing, right? And furthermore, you don't know the parameters of some of the data generating process that may have generated it, you can either, sort of jointly solve for the missing data and your missing parameters and find sort of the things which are most likely or maximize the likelihood of what you've observed. Right? But that's usually pretty computationally expensive. So instead, you can basically first either guess some parameter values for the parameters and then fill in your missing data based on those parameters, or the other direction, first guess some values for the missing parameters and then compute the maximum likelihood estimators of your parameters and go back and forth, right? And that's just what's called expectation maximization, right? So, I'm not going to say anything more about this because if we would have had like 5 more minutes, I might have, right? So to make this slightly less hand wavy. But the point is, expectation maximization just says, fix your parameters, estimate your unobserved data, in this case, which cluster every particular point came from. And then maximization says, fix which points are assigned to which clusters, find the MLE for the parameters. And in this case, the parameter is the center of the cluster. And then go back and forth. Okay? So this is a sort of meta algorithm for sort of jointly solving some minimization problem where you have missing data and unknown parameters that were generating that data. And if it's computationally too exhaustive, to find the global minimum jointly. You can sort of fix one, minimize the other, fix the other, minimize the, this is exactly what Lloyd's algorithm is doing. And just like Lloyd's algorithm, chances are this won't always converge to the global minimum of your problem, right? But it is, it is a way to solve this joint optimization problem, at least approximately. Okay, so that's all I wanted to say. And we fit nicely into 80 minutes today, so go us. And we'll stick around for some questions.